and the refractive index of glass. And when you talk about the refractive index of glass, you're just saying what would happen if it went from a vacuum into glass. Do you understand? Yes? Yes? You understand? So you can talk about the refractive index of glass, the refractive index of water. Agreed? Happy? Yeah? Rather than here, we're talking about the refractive index as it goes from one into the other. So in terms of the actual individual refractive index, it's the other way around, okay? So it's equal to N2 over N1. So sometimes they might give you the refractive index as it goes from 1 into the 2, yes? Or they might tell you the refractive index of medium 1 and the refractive. They could give it to you either way, yes? Happy? Got it? We'll do some questions in a minute. All well and good? What stays the same as it crosses the boundary? What stays the same? The frequency, exactly right. Because everything changes, but one thing does stay the same. The number of waves go. Hello? I don't have one. I use my head because I'm so clever. So as they go from one medium into the other, obviously the number of wave fronts arriving every second, what goes in must come out. So the frequency never changes. And that means if it's light, it will go in at green and come out at green, yes? It will go in red and come out. So the one thing that stays the same is the frequency. So if they slow down, what's happening to the speed? The speed is going down, the wavelength's going down, but the frequency is remaining the same. What would happen? Okay, got it? Very quickly, we'll go on, yes? Happy? We're doing it very quickly so I can get on to past paper questions. Now, let's have a look at the far more interesting situation, all right? Because we're so used to going from air into glass, slowing down. But it's far more interesting to ask what happens if it's trying to escape. Okay? So what happens if this was the glass and this was the air, okay? And this time the wave fronts are coming in this way. Agreed, yes? This is the incident wave fronts. Got it, Noor? Yes? But now be careful, because now they say that this medium, C1, and this is C2. Agreed, yeah? But now, Noor, the waves are going to speed up. Whereas when waves slow down, they always succeed in crossing the boundary. When waves speed up, they don't necessarily succeed in crossing the boundary. So watch out for the far more interesting situation, yes? Where waves are trying to go from a slow medium into a fast one. Not from air into glass, but from glass into air, yes? Watch out for that. Alarm bells go off, because they don't always succeed in doing what? They don't always succeed in escaping. By the way, if they do escape, what's going to happen? Think of our wheels. Which wheel's going to hit first? This wheel. This wheel's going to speed up, isn't it? Yes? So if they do succeed in escaping, the ray is not going to continue in a straight line, but the ray will bend this way. You don't need to learn rules, yes? Just, yeah, got it? If they do succeed, then the ray is going to bend, and the ray is going to bend, which way? The ray is going to bend this way, yes? Agreed? Because that wheel speeds up first, and it swings this way, yes? And because I've speeded up, what's going to happen to the wavelength? The wavelength will get longer, yeah? Happy? If they do. Sin I, this angle is R, yes? Once again, sin I over sin R is going to be equal to C1 over C2 is going to be equal to lambda 1 over lambda 2 is going to be equal to the refractive index from 1 to 2. But now the refractive index from 1 to 2 is not going to be greater than 1, it's going to be less than 1. Agree? Happy? Same thing applies, same rule applies. Got it? But why have you got to be a little bit careful? I'll speed up. Okay, why have you got to be a little bit careful in this case? Because there's no guarantee that the ray will escape at all. There's no guarantee. Rays coming in from fast to slow will always cross the boundary, yes? But waves trying to escape from slow to fast don't always cross the boundary. It all depends on the critical angle, okay? There is a particular, and you did this yourselves, guys, yes? As you increase, you did this with your ray box, as you increase this ray comes down, 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 yes? And you can find you did this experiment, you did it, you can find a particular angle of incidence, yes? For which the ray just, can you remember this one? You increase it slowly, 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 you use the semicircular block, yes? And there becomes a particular angle where it just escapes, yes? Now clearly, if you go any more than that, you're going to get total internal reflection. If you go any less than that, it will escape. Do you understand? So will it escape or won't it escape? Got it? To answer that question, you simply have to, if supposing they say that this is an angle of incidence of 50 degrees, will it escape or won't it escape? You have to calculate the critical angle. If the critical angle, if this is greater than the critical angle, total internal reflection, okay? So how do you calculate the critical angle? Is there a formula in your data book for calculating the critical angle? Answer, no. But what you can do is you can use the result for the critical angle, because this is 90, yes? Yeah, because this is 90, then sine I over sine R is going to be equal to, what am I doing?
Sine I over 1.
Is the refractive, sine is the refractive index, yes? Yes? Yeah, Sine I over sine R is the refractive index, agreed? So what's the critical angle? Well, look, if this is the critical angle, if the angle of incidence isn't just any angle of incidence, if it is the critical angle, what do you get? You get sine C. So generally speaking, are you agreed? Sine I over sine R is always equal to the refractive index, right? Yes? So up from this medium into that medium, yes? They'll give it to you, maybe 0.8, yeah? Agreed? They'll tell you the refractive index this way is 0.8. This way it's always going to be, do you understand? They'll give you the refractive index, yes? How do you calculate the critical angle? Well, you simply say it's always true that sine I over sine R is always equal to the refractive index. But if you want to find the critical angle, it follows that if I is not just any angle of incidence, but if I is the critical angle, then what's the angle of refraction? 90. And sine of 90 is 1. So it automatically couldn't be easier. The critical angle, yes, is always going to be equal to the inverse sine of the refractive index. So if the refractive index here, they'll give it to you, yes? Yes? If C1 over C2, lambda 1 over lambda 2, yeah? Well, yeah, if that's equal to 0.6, that's all you need to know. Agreed? Yeah? So if you know the refractive index, you can easily work out the critical angle. The critical angle is just the inverse sine of the, so in this case, the critical angle would be the inverse sine of 0.6, agreed?
0.6 is the ratio.
Is the refractive, yes, exactly. Remember, you were a bit late coming, so remember the refractive index is lambda 1 divided by lambda 2, C1 divided by C2, sine I divided by sine R. That's the refractive index. I've just written it down, okay? Lambda 1 over lambda 2 equals C1 over C2 equals sine I over sine R. All I'm saying, Hamza, is if you know the refractive index, you can really easily work out the critical angle, yes?
Yes.
Because the critical angle isn't just any old angle of incidence, it's the angle of incidence where this is. If this I is now the critical angle, then R by definition is what? It's 90 degrees. Do you get it?
Yeah.
So, happy? Summarize, yes?
What if the refractive index is greater than 1?
And the refractive index can only be greater than 1 if the light's going the other way. Agreed? If the light's going from from fast to slow, it'll be greater than 1. If it's going from slow to fast, it'll be the inverse. Agreed?
Yeah.
If the refractive index coming this way is 1.4, the refractive index going is going to be 1 over 1.4. It's flipped around, yes? Agreed? You happy? Yes? Happy? Let's go into, yes.
I have a question. What was the sorry, when it goes into when it slows down, going into another medium, the refractive index of that medium is smaller, right? When it slows down, going into another medium.
Yes. I mean, you missed the beginning.
Yeah, sorry.
Okay. So if it's going from medium 1 to medium 2 and it's slowing down, then what's going to happen to our waves? They're going to hit like this and they're going to bend.
Medium 2.
They're going to bend towards the normal. Agreed? Yes? Happy?
Yeah.
So lambda 1, lambda 2, when it's slowing down, yes? Lambda 1, lambda 2, sine I, sine R.
Yeah.
What's that ratio going to be when it's slowing down? When it's slowing down, lambda 1 is always going to be bigger than lambda 2. So the refractive index when it's coming this way is always going to be bigger than 1. If it's going the other way, it's just going to be the inverse. Do you understand? Less than 1, yeah? Happy? Okay, so can I go straight into questions, which is what Hamster wanted. But what was my document? Waves. I thought I had this document. Okay, guys, I want to go. Let's put it into practice for you. A lot to do. So Hamza wanted to do more past paper questions.
Yeah.
So we can do that. Where is this document coming up? Here. I did. Oh, I wasn't in the right document. Okay, so questions on this are quite rare. Okay, but I'll do this one here. How about this one for refractive index? Okay, a light ray passes from air to water. Any need for alarm bells? No. It will always succeed in going from fast to slow. What can we do very quickly in our revision answer? We can say to ourselves, let's think about it a little bit. What do we know about it? We know that there's a lambda 1 here, yes? And when it goes, what's going to happen to the wave fronts? They're going to bend towards and they're going to get closer together, agreed? Yeah? And so what do we have? This is the ray. We have I and we have R, we have lambda 1, we have lambda 2, we have C1 and we have C2. And what do we know? Lambda 1, notice when it's going this way, lambda 1 over lambda 2 is going to be greater than 1, yeah? And C1 over C2 when it's going this way is going to be equal to sine I over sine R. And this is called the refractive index from 1 into 2. And so when it's going this way, Kareem, are you with me? It's going to be like 1.4. What happens if it's going the other way? You understand? Then everything is reversed. So it'll be 1 over 1.4. But in this question, what's happening? Let's go back to the question and look at some discipline. What are the changes? Let's clear that one up because you wanted to do past paper questions, yeah? So what are what's the change in the wavelength of the light? Please have the learn safe. And the change in the angle of the ray makes with the normal. So what's going to happen to the wavelength? Well, that's going to decrease. The angle is also going to decrease. It's going to move, swing around. No, that's a very easy one, yes?
Yes.
Are there any other ones? I wanted to find one which was really good. And I swing through here. And here's another one, multiple choice, and I'm going to do one paper, 2 question, right? So let's have a look at this one. A light ray is incident on an air diamond boundary. But what we've got to worry about really is which way is it going, yes? And what do they say? The refractive index of diamond is greater than 1. Obviously. Which diagram shows the correct path of the ray or light ray? Diamond, so could this be correct?
Yeah.
This could be correct, right?
Yes.
This could be correct. as long as this angle of incidence here is greater than the critical angle. That could absolutely be correct, yes? What about this one? Nonsense. It's A, yes, it's A. But I would like to give you a question which is on an ice cube, and it comes a little bit further. I wrote them all down on a piece of paper and then I lost the piece of paper. I'm looking for a question with a picture of an ice cube. I did, honestly, I wrote them all down on a piece of paper and then I lost the paper, so now I'm having to waste time doing it like this. Never mind.
This is a drug deal.
Here. All right. This is actually the only paper 2 question.
Sorry,
You've done a question 5 times.
It's the only question that's in
Mr. Chris, last year there was a past paper.
But it's actually a very good question, yes?
I said that.
So just
I had the paper too.
we go to soda. Do you want me to go over it? I think it's worth it because it is a very good question, yes? Because everything's here. Everything's here. So a large ice cube is formed from ice, fair enough. It looks like a square to me. A light ray is incident from a vacuum at an angle of 46 degrees, yes? Okay. Now a vacuum has a refractive index of 1, okay? So a cube. The light ray is parallel to the plane, and everything's in the diagram, isn't it? Yes. Yeah. It's all in the diagram. If you like diagrams, and I do. What can we do with the information here? Well, it's like gases. They kind of give us the complete state here. We know I and we know R, and so therefore we can work out the ratio of lambda 1 to lambda 2, sine I over sine R, C1 over C2, and we can work out the relationship of the refractive index from a vacuum into glass. Yes? Yes? We can work out the refractive index of the glass. So that's obvious, yes? We also know C1 because it's a vacuum. So C1 is 3 times 10 to the power of 8 meters per second, yes? So immediately I can see where this is going, Hamza. I can find out the refractive index here. Now I know the ratio of lambda 1 to lambda 2 and C1 to C2, but I already know that. So this is going to be slower than the speed of light, yes? Because it's gone into a new medium. Calculate the speed of light inside the cube for 2 points. Well, it might seem a bit mean, but what can I do? I can simply say sine of 46 divided by sine of 33 must equal to C1, 3 times 10 to the power of 8 divided by C2, yes? And then you calculate the speed inside here, yes? Yes?
Is there any case where it's N2 over N1? There is a case.
Yes, there is. But, okay, you arrived late again.
What do you use?
I'll come back to it at the end of the question, but remind me, yes? Okay, so let's go on. Show that, for 3 points now, show that no light emerges from side AB. I love this question because everything is here. You hear me? So we now know, well, what about this? We're now talking about AB. So what are we going to do? Well, light's going to travel in a straight line, yes? But now the alarm bells are ringing, right? Why? First of all, now the refractive index, whatever it, what can someone do? What was sine 46 over? Could someone do it on a calculator? What is the refractive index? Whilst I just modify this diagram.
I could do this with radians.
What is the factor?
I mean,
Sine 33.
1.3.
Sine 46.
1.32.
1.32. And therefore, at this border,
It's 1 over
the refractive index is going to be, which is what?
which is 0.76.
0.76. You wanted to do questions. I hope this is giving you what you wanted. Yes? Yes?
Yep.
Now a bit of geometry. Because they say show that it will or show that it won't. I think it might be better saying by doing a calculation, show whether it will or whether it won't. I know because of the geometry here that this angle of incidence is going to be 57.
Correct.
Because it's, yeah, I know by geometry that's 57. So question is, will it or won't it escape?
You have to find the
Well, I simply want to know now whether 56.7 is bigger or smaller than the critical angle. But now what do we remember? We remember that the critical angle is equal to what? The inverse sine
of 0.67.
of
76.
the refractive index. That's not in your data book, so if you want to remember to learn that before you go into the exam, yes? Or you can memorize how to do it. So what is sine minus 1 of 0.76?
49.
Thank you very much. 49 degrees. So the critical angle is 49 degrees. This is coming in at 57 degrees. Guess what?
Internally.
It's going to be totally internally reflected. Now we are in a position, that means it's going to bounce off here at what angle?
57.
57. And so now what's going to happen when it hits this side? When it hits this side, this angle is going to be 33. Do you understand?
Yeah.
And will it escape from this side?
Yes.
Yes.
Now it will, because 33 is less than 49. So now it's going to escape. And as it escapes, can we calculate this angle here? Yes, we
It's
can.
right there on the left.
But it's all, or it's already going to be. Do you see what I'm saying? Do you get what I'm saying? It's a very good question. It's a very good question, and it's one that's worth going over. Now, that's how the whole question goes. Incidentally, where's Leanne? Okay, Leanne said, I'm listening to requests. She said, could you go over more questions where different topics are thrown in? And this is a very, very good one. It starts with critical angle, and then it immediately works into each side of the cube. It's the length of the cube. Yes, it's a cube. So by giving us the lengths, we know the volume. Yes, the initial temperature of the ice cube is minus 20. Determine the energy required to melt. I'll do this one with you, even though, because you requested this, okay? Determine the energy required to melt all of the ice from minus 20 to 0.
MC delta T plus L.
No, watch. I don't know how. Now let's revise it. I always think of these ones in terms of a graph of temperature versus time, yes? So what does our ice cube start?
أنا جبته صح.
So they're asking us to determine what? The amount of heat that I'm going to have to put in to turn it from a block of ice at minus 20
Just water.
to a puddle of water at 0. Now we did this. How many stages of heat are going to have to go in? Think of the temp. Yes, well done. The first is going to take it from minus 20 to 0. And that heat is specific heat, agreed?
Yes.
But then the next load of heat that's got to go in is latent heat. You got it? So you've got to work out, first of all, the specific heat, which you'll find by MC delta T, agreed? Do you know the mass?
Yes.
Yes, because they've given you the volume and the density. So you can find the specific heat needed to raise this temperature, because you know the mass, you know the specific heat, yes? And the change in temperature is 20. And then you've got to work out the latent heat, and if you remember rightly in your data book, that's L times delta M, where delta M is the amount of mass you've melted or boiled, yes? You got it?
Yes.
Okay, Leanne? So that's a good example, completely fair. And then finally, we've outlined the difference between the molecular structure of a solid and a liquid. It's only 1 point.
Uniform.
You know, solid,
So
they're
it's
stationary and
vibrate,
vibrating. Liquid, they're moving more freely. Happy?
Yes.
Right. So, next thing we're going to do, Doppler effect. I want to do this very quickly. We're doing well. Is this a better balance?
Yeah.
Yes? Okay. Hamza, if you want to stay behind at the end and I'll ask your question about N1 and N2 and N12, ask me at the end because you missed the beginning. Okay, guys? Good? So let's now go on to the Doppler effect. I'm going to do a crash course of the Doppler effect. First thing you need to know about the Doppler effect is meow, okay? What is the Doppler effect? Think Sheldon. In the Big Bang Theory, remember?
Yeah.
Meow. If that's kind of a learning disorder, I think it's really out there. You know that one?
We should watch it together.
No, we haven't got time. Okay, meow. What is the Doppler effect? It's almost pornographic. Take a seat. All right. Okay. Okay. So let me get on with it. By the way, why? Majid, why I'm a bit in a hurry because I've got to do refraction, I've got to do the Doppler effect, then I've also got to do all of the interference ones and past paper questions, right? So, can you settle down? So, the Doppler effect, what is it? It's the apparent change in frequency, yes? Because of movement, now you've done relativity, you'll understand.
Yeah.
Relative movement between the observer and the source. Yes? Agreed? Now, next thing you really need to know is when you look into your data book, you're going to get not one, not two, but you're going to get 3 formulas. The first 2 formulas are for mechanical waves. Light, mechanical waves, sound waves, water waves, earthquakes, any mechanical wave, yes? The third one is for light. And let's go to the data book, yes? And then we'll put it in practice. Okay? So, if I go to a new screen. And then we'll look at some past paper questions. Again, quite rare here, yes?
Should we expect them on our
Multiple
exams?
choice is where they're normally going to come up.
Okay.
Physics data book, your data book, let's see how they're presented to you in your data book, yes? So where are we? We are on wave behavior, and it's advanced higher, I think.
Yeah, it's under.
And so where are we? Where are we?
The other equations are
down
down.
next
Because
page.
there's one standard, for the light is on standard.
Okay, so here, okay, now, okay, good point. Good point. That's why we're here, right? You will find 2 of the equations here in the advanced higher level. These are the equations we use for sound waves and so on and so forth, water waves, yes? You will find the 3rd Doppler shift equation back here in the core. This is the equation we use for light. And don't panic because it's in core, right? The Doppler shift for light, I'll explain the revised review in a minute, is very much easier than the Doppler shift for mechanical waves, all right? Happy? So let's have a look at how they're presented with you in the data book. First of all, you'll see there's an equation for moving source and there's an equation for moving observer. So the first thing you have to do in these questions is you have to ask yourself, is this the source moving or is it the observer moving? Yes? The second one you have to use, say, is do you think the frequency will go up or will it go down? And you choose the appropriate plus or minus. In this one, in this formula, U is the source and the observer, and V is like the speed of sound or so on and so forth, all right? You got it? Happy? And what the subject of the formulas is the actual frequency you will hear. All right? Happy? So let me quickly go back to and give you an example off the top of my head. Okay? Abdullah, let's go. Right. Sound is the boring one, right?
Yes.
So but we'll start with sound. So supposing, and I want remind me to do a double shift. Very important. You'll see it coming up in the multiple choice. I'm going to give you a difficult multiple choice, all right? Okay, so here is the observer, and this is sound. So I'm going to draw a really big ear. That's supposed to be an ear. This is the observer, yes? And what we've got is we've got an ambulance moving towards him, yes? And with a horn that's going me with a particular frequency, yes? Now if the ambulance was at rest, what would the wave fronts look like? Perfectly circular, isn't it? Me. Yes? These are the wave fronts. If it was at what? If it was at rest. Just like if it was water waves, you're just doing this, what are the wave fronts going to look like? Yes? So, yeah, like refraction, the Doppler effect is explained in terms of wave fronts. Okay? Now, it doesn't take a lot to realize that if the source is moving, or if it was a swimmer, or something like that, I'm trying to clean my diagram off here. It's very reluctant to... Okay, because the ambulance is moving, what's going to happen is that the waves are going to look like this, yes?
Yeah.
Now they're still going to be circular, right? They're still going to be circular. It's a bit difficult to draw. Okay, you get it? You're
Yeah,
happy?
yeah.
They are still going to be circular. People tend to draw these like eggs, but they're not, alright? The wavefront is created, it's going to spread out as a circle, agreed? Happy? But the important thing is, ahead of the moving source, the waves are shortened, and behind they are lengthened, agreed? Yes? But in the Doppler effect, we're talking about what frequency. Now, the actual frequency of the horn is F0, yes? Agreed? Clearly, the faster the source moves, and in your data book that's U, agreed? The faster the source moves, the effect becomes what? Bigger, yes? The faster the source moves, yes? So how much the effect exists is going to obviously depend on the shift, in other words. The frequency you hear is going to depend on the speed, yeah? Happy? I've got to go very, very quickly. Now, listen, okay? Let's plot. They might happen in a multiple choice graph. This is the frequency you hear, all right, versus time. Okay, stay with me. I'm making up an answer. I'd like to show you this is a multiple choice question, all right? It is. Treat it as a multiple choice question. The graph below shows how the frequency. Listen, it says that an ambulance comes to. I'll just move on if you only want to.
Source,
The ambulance moves towards the observer, passes him, and then goes on. And this graph shows the frequency that the observer will hear as the ambulance comes towards him, passes him, and moves on. And what's included at this point here is F0, which is the actual frequency of the horn. Agree? What's this graph got? How the frequency changes with time. As the ambulance comes towards him, well, we know he's going to hear meow, all right? So as the ambulance comes towards him, he will hear a frequency which is higher. And then as it passes him,
Straight line down.
it's gonna
Like
not a
with a
straight
slope,
line. It's gonna be
like
like
with a
that. Do you
slope.
understand? Yes.
Yeah.
And then as it goes away, it's going to be less.
On a straight line.
Is everyone happy?
Okay.
And just straight. Do you know what? I don't know. Okay, you got it, guys.
And at
Yes?
which point will you hear the actual?
I can't take your question because there's so much going on here.
If the speed increases, how would the graph change?
Okay, they won't ask. Okay, I don't want to get hung up on
Better.
it. No, please, Kareem, let me speak because I want to go into more detail. And everyone's just stopping me. You want hard questions,
Yeah.
so I want to go into hard questions, but this is stopping me going into hard questions. I'm just stuck at a basic level. Okay, that's option A. I'm telling you right now, if I was writing this question, I would include this as an option B. I would include this.
Yeah.
Because people get confused with frequency and amplitude. Because as the ambulance is coming towards you, the loudness will increase. Do you understand? This is wrong. Because the ambulance is going at a constant speed, as it comes towards you, you'll hear the same sort of big me. Yeah? Not me. Yeah? You just hear me. Do you see why they're going to include this one?
Yeah.
Because they're going to trick you. What you actually hear is the loudness going up and then the loudness going down. But the frequency. Oh, do you know? I don't know. You want me to get onto harder questions, and when I give you a harder question, you won't turn off and you don't think about it, right? Okay. So let's go back to how you'd actually calculate it in this one. Well, what formula you're going to need to do in this one. And the size of the shift is going to depend on the ratio. This is very important. The ratio of the speed of the source to the speed of sound. All right? Do you get it? That's a big factor. If you want to do a rough, if you want to do a rough, if you don't want to use the formula, supposing the actual frequency was 500 hertz, yes? And they tell me that this one is moving at a speed of 33 meters, yes? Now, if I want to find out what frequency he's going to hear, I'm actually going to have to use the formula, which we will do in a minute. Agreed? But I can do a very, very quick estimate, and I'm going to get very, very close. Because the size of the shift depends on the ratio of the speed of sound, the speed you're moving compared to the speed of sound, yes? And you're moving at 33 meters, and the speed of sound is 330 roughly. So I immediately know that the ratio of the speed of the source to the speed of sound is going to be about 10%. And therefore, and I know it's going to be shifted up. So I'm going to, originally it was 500, back of the quick guess is going to be approximately you're going to be hearing approximately 550. Do you understand? You see where I'm coming here? This is very quick, back of the, and it always works if you're in a hurry. And it helps you in multiple choice, yeah? Because they might say, which one of these things? Yeah, and it's 10%. Agreed? Happy? Do you see what I'm saying? Yeah. But let's now work it out. If you want to work it out using the data books, let's see how we would do it. Who's got a calculator?
Yeah.
This example. What have we got? What are we on? We're looking at moving source. And so we need to work out this number, yes? You've done relativity now, it's like a Lorentz factor. So what is V? Let's take that as 330, yes?
Okay.
Divided by, and what do we want to use here? The frequency's got to go up, so we need to use the minus. So 330 minus, in my example, 297.
If the frequency is going up.
In my example, what did I say?
The speed of the source was 33.
This is 330. And so what are we going to get down here? 330 minus 33, which is 300, yes?
Wasn't the speed of it 33?
297 down. Yeah.
Oh, God.
Okay.
Could someone just...
What is the original frequency?
Oh, 500.
Okay. So the new one is
So what is-
555.
So what is this? Stay here. What is this? V is what, in my example?
330.
330. V here is?
330.
330.
Minus 33.
I use the minus because the frequency's got to go up, and US was 33. So I was right. This factor becomes 330 divided by 297.
97.
1.11.
And this factor is 1.11. And therefore, the frequency you'll
It's
hear
555.
will be 500 multiplied by 1.1, which is what?
555.
555. And what did I guess it as? What did I
550.
guess it as? Approximately a 550. I'm close, right?
Yeah, very.
Happy, guys? Yes? Now, the reason why I'm saying the guessing business, by the way, if it was moving towards you, moving source, you've done all this. Okay?
Yes.
The reason why I'm saying about the guessing business is what about light? That third equation. Okay? What about light? Well, the thing is that light's in the standard level, right? So it's got to be easier, right? It's got to be easier. Now you've done relative. Oh, by the way, how was the ear being tricked in my last example? The frequency you hear, frequency is speed divided by wavelength. Can you remember this? Your ear can be tricked two ways. Either by the wave fronts entering at the wrong speed or them entering at the wrong wavelength. In my last example, you were just standing still. And so the sound was entering your ear at the right speed, but too short.
Yeah.
What would happen if the source was stationary? And you were moving towards the source. Now, how is your ear being tricked? Now they're entering at the right wavelength, but now you begin to get it at the wrong speed, because these are traveling this way at 360, and you're traveling this way at 30. In your frame of reference, how fast are they approaching you?
309.
Yeah, do you understand? They're now the wrong speed. Do you get what I'm saying?
Yeah.
So these are the two ways. So why do we need a new way for okay, stay with me. So I'm just trying to get so much done in the session. So red, which way do they go? Green, amber. Okay, answer. We'll do some, right next we're going to do questions, right? So stay with me. They're coming up. Hard ones. So supposing now it's light and you are driving towards a traffic light, yes? Okay. And the frequency of the red light, they might tell you the frequency of the red light is whatever it is.
900.
Frequency of red light. Frequency of red light.
Oh,
It might
frequency.
be 9
Yeah.
times 10 to the minus 12 hertz, or something like that. Yes.
Yeah, okay.
The frequency. Yes. How can you find the frequency of red light? Speed
divided by
divide. Yeah. So they give you the frequency of the red light. Yes. Happy? Remember? Yeah. You see the problem? Well, there's going to be no. But what's the problem? Because now the observer is your eye, not your ear. But your eye can't be tricked by light entering at the wrong speed. Remember, from relativity, light always enters at the right speed. Do you understand? So we need now a completely different formula, because your ear can be tricked by the speed of sound entering at the wrong speed, but the speed of light always enters the same. Do you understand? So we need a different way of looking at it. Happy? But here's my trick. Here's my trick. Supposing you were driving at 0.5 C, a very fast car. By what fraction? What's going to happen first of all to the
It's gonna
frequency?
shift 50%.
You're driving towards it, so the frequency is going to
Shift up.
shift up. Yes.
Yeah.
That's not a problem because it's going to become more yellow. Yes.
Okay.
If you were driving away from it, what would happen to the frequency?
Go down.
Meow, yeah. The frequency would go down,
Infrared.
and in your rear view mirror, you wouldn't. It would become invisible. You wouldn't see it in your rear view mirror. That's a bit curious. Where's it gone? Basically, it hasn't gone anywhere. It's just that the light has now been shifted down, and below red becomes infrared, which your eye can't see. Do you understand? As you're travelling towards it, you're going to say, but how much is the shift going to be? We don't need one of those complicated formulas. We don't need one. This is why it's so easy.
This is V over C.
I remember in the Doppler effect,
Yeah.
I always said that a short estimate is how fast are you going relative to the speed of sound, yes? That's just an approximate one in mechanical waves,
Exactly.
but it's the actual one in light. That's why it's so simple, yes? If you want to know what happens to the frequency, how fast are you going relative to light? 0.5. And so this will be increased by 0.5. Do you understand? So this will be this value plus, it'll be increased by, yeah? What happens if you're going at 0.7 C? What frequency will, the change in the frequency is simply equal to V over C.
Correct.
So if you want to know how much the frequency, yes, by what fraction will the frequency be increased? It's that simple, yes?
Or decrease.
It is that simple. Just like it, yeah. So in your data book, guys, yeah. Yes? I don't know.
ضبط شيء هو عشان تعرف الشيفت يعني
Okay, so where's that in your data book? Where's that in your data book? It is where? It is. Do you want to go on? I can if you want. Let's just stop it because no one seems to be, So this is the formula in the data book, yes?
Yeah.
But notice the formula of this one is not the actual frequency you'll see,
It's a change.
it's the change in frequency. And all this is, the IB do write formulas in stupid ways. The best way to write this formula would be the change in the frequency will be equal to VC times F. So if you, I don't know, to me it's obvious.
Yeah, yeah.
If it's
Yeah.
not obvious to you, then you should be doing standard level physics, but honestly. So if you're traveling at 0.3 C, how much will the light be shifted by? 30%. Increased or decreased by 30%. If you're traveling at 0.7 C, how much will the light be shifted by? It'll be increased or decreased by 70%.
So what does the light particle see?
we don't go there. Okay, so let's, because I want to push on. Yes, Hamza.
If they ask us how long would the light take to go and come back, what do we do to the change in frequency?
I don't understand the question.
وين لما يحكي لك السؤال شوف question down.
هذاك إشي تاني.
What that in years? It's 3 light years away بعدين.
ما بحكي عن تعرفين light. لا stop it.
I'm trying to find a question, okay, which I want to deal with, because that's basic, quite honestly.
Mr. Chris, there is one up where it's like Doppler shift, but it's decelerating while it passes you.
It doesn't tell me, because I don't have that question available, yes? Okay, but feed it to me, give it to me, send it to me, but right at the moment I can only do what I've got. Okay, what we could do now is we could spend 15 minutes whilst you find the question that you're talking about, and you give it to me, and I can read it, and in 15 minutes time I'll write it on the board and we can all discuss about it, and then we've wasted 15 minutes. It's not going to work that way.
It's on the document, that's why I'm
I
asking.
meant this
What do you want me to do? Go to my computer right now and try and find the document and we'll whiz through it and find the document and then go. Do you want to do that? I don't mind if you do, but it's going to waste 10 minutes. What do you want? Do you want?
It's fine.
I don't know. Here's my laptop. Find it for me. Or I can find it.
This was the question.
This is a question I want
Just
to
what I'm
ask.
saying. I'm trying to get a lot of stuff done here. But by all means, please, if you've got these questions, I did post on the website that we're going to be doing this stuff in the Doppler shift and stuff like that, right? So the best way, I mean, I'm not saying I won't do these questions, but why don't you come to the class with these questions ready prepared, yeah? Or email them to me, yes? I will willingly do them. But I can't just right now just say, Mr. Chris, there was this question here, here. It's going to take me 15 minutes. Agreed? Well, I can if you guys want to, but okay, let's go to questions, yes? Do you see what I'm saying, Cream? Send them to me. So please use radar to detect speeding cars. I'm going to do 2 Doppler shift questions. Okay. A police officer stands at the side of the road and points a radar device at an approaching car. These 2 questions are all going to have the same thing in common. The device emits microwaves which reflect off the car and return to the device. Got it? A change in frequency between the emitted and received waves occurs. Yes?
Mm-hmm.
Why? It's a Doppler shift, isn't it? I send out a signal like this, it bounces off the car and it comes back at a different frequency. What topic are we here? This is Doppler shift, yes? But the difference here is what? In the previous examples, we've just been dealing with I'm stationary, either the thing's moving towards me or I'm moving towards it. You'll see in the next 2 questions
Both are moving towards.
that no. You wanted difficult questions, so I'm going to give you. I've chosen these difficult questions. So what's happening here? I'm standing, right? And I'm sending out a signal. Let's call that F0, 500 hertz. It's going to be much higher than that. This is light, okay? The car is coming towards me, all right? So what happens first? The light hits the car, yes? But then the light is reflected. Do you understand that there are going to be 2 Doppler shifts here? 2 in succession.
That's what I was asking.
Okay, so yeah, that's why I'm going to go on. So think about the car, the guy in the car, yes? What approaches him?
The wave, microwave.
Okay, let me just, okay. What he sees coming towards him is a signal. Is it going to be 50 hertz?
No.
I sent out a signal of 50 hertz. What's the guy in the car going to receive? Not 50 hertz.
Something
There's
different.
going to be a Doppler shift.
Yeah.
He's going to receive a frequency which is higher than 50 hertz. And if it was sound, you can calculate that using the formula. Agreed?
Yeah.
But then what?
It's going to be reflected.
Then he takes that signal, which is now 55 hertz, and he emits that. So what do I end up receiving?
Something even
That
greater.
55 hertz is shifted
Again.
again. There's a double shift. Do you see what I'm saying? It's exactly no. It's shifted first when it's received, and then it's shifted again. What kind of shift is the first shift? It's moving source. What kind of shift is the second one? It's
The first one is a moving.
Moving
the
source.
first one is a moving observer.
sorry. The first one is moving observer,
Yeah.
and then he takes that frequency, he chucks that frequency out, and the second one, that frequency is then shifted again. Are you with me? And that's now moving moving source. Got it?
It's a microwave. So
But the
it's not
point I'm
energy.
Hamza, the point I'm trying to make is that this is more complicated because it's an echo, a reflection, right? All you've really got to remember, and you're clever enough to do this, is that there's a double shift. Agreed? Happy? Now it's particularly simple for light. Listen, it's particularly simple for light. Because if this car was traveling at 0.7 C, all right, and the signal is sent out at 500, all right, the first shift
Would be 7.
is going to be increased by 70%.
And then another 7.
So 500 increased by 70%. What is 70% of 500? 350. So, but the first one is going to be 850. Then that 850 gets done, and the second one is going to be shifted again by 0.
Yeah.
It's very easy in light.
144.
Agreed? Do you understand my
Yeah,
sums? Yeah. But it's going to be a little bit more what? A little bit more complicated in mechanical ways. Watch the next question. So this question, by okay, Hamza, let's go through the question very quickly. The frequency change is given by this formula, V over C. Why the information given the transmitter frequency is this? Yes. The maximum speed allowed is 28 meters per second. All right? Okay. Yeah. The car. And explain the reason for the frequency change. 3 points. Explain. You can't just say the Doppler shift. That's not an explanation. You can say this is the Doppler shift of light. No, because this is a radio wave. Radar device. The device emits what? Microwaves. So you've got to say this is a Doppler shift. It's a double Doppler shift, but not of mechanical waves. It's a Doppler shift of electromagnetic waves. Okay, agreed? Happy? And actually not one but two. That will give you 3 points. Then what's the next one? Suggest why there is a factor of 2 in this equation. Well, because it's shifted twice.
Yeah.
But if it was a mechanical wave, you'd have to find the first shift.
And then
You'd have to use one formula. And to find the other one, you'd have to take that and use the other formula. But because it's light, it's just very much, it's the same shift every time. Because it doesn't matter whether you're going towards it. And the shift will be whatever it is. Do you understand? And then finally, determine whether the speed of the car is below the maximum speed allowed. Well, that's just a straightforward application of what? Application of the formula. Because they've told you the shift, they've told you this, you know this, and it's just finding the speed V.
And then if it's
And
greater than
then
the
it'll be
maximum
less
speed
than
allowed.
28, yeah?
Yeah.
So that's actually really, really easy, okay? Got it? Happy? And then it goes on to something, it shifts into something which is no longer on your syllabus. All right? I hope I'm doing okay. I've selected these ones because you wanted difficult questions. I think that was a fairly easy one, but not questions if you... Yes, Alan.
If it was moving at 0.7 C,
That is it.
it was
A bit down. That's the one. Well, I
Okay,
think it is
right.
what it is.
Thank you, Kareem. This is the one you're talking about.
I think it's similar.
It's
yeah.
similar. Let's have a look. It's another Doppler shift question, yes? It's not what I wanted, but well done. Well observed, yes? Similar, hopefully, yes? Well, yeah. Let's have a look. A train moves at a constant speed whilst emitting a sound. A wave of frequency F0. That's F0, yes? Okay? This is just what I discussed. The train passes through a station, which means it comes towards and passes through. Agreed, yes? Which graph shows the variation in the time of the frequency measured by an observer standing on the platform. The train is always travelling at a constant speed, yes? So why is this wrong?
Because it's not the
So this first of all, this is wrong on so many points. But basically, sorry?
We do.
Mr. Casey, what if the car wasn't moving at a constant speed, it was accelerating?
Or decelerating.
They should not ask that. Because
Okay.
it does say in the syllabus that they should. But if you've got a
Oh, 'cause
question,
it-
bring
yeah,
it to me
yeah,
tomorrow.
absolutely.
Why is this one wrong? Obviously wrong, yes?
Yeah.
This one is temptation. When you look at the examiner's report, I bet you quite a few students said this. Because on the one hand, it shows that higher and then lower.
That would be the
And
amplitude.
it also, yes, exactly, it would be the amplitude. And if you think about it, it's ridiculous. Yeah, so that's ridiculous. This is completely ridiculous. Yes. And
Yeah.
this is the correct
So
one.
I'd love to see the
Yeah.
discrimination
Yeah.
index.
Yeah.
of this one.
So Chris,
Yeah.
if it was accelerating, it would be A, right?
Yes. A would be if it was no.
Okay, the
A
column.
would still not be right. I think if it was accelerating.
How
But I want
sure
to.
would
I want to do. There. My brain is. I'm trying to get as much done as possible. Here we go. You wanted hard questions on the Doppler shift
Oh, I
because we
see.
need to get to sevens. Yes. So this